Hello, everyone. A warm welcome to this first session in the Reproductive Toxicology webinar series hosted by AIRA Matrix. My name is Dr. Uttara Joshi. I'm a surgical pathologist and I head business development at AIRA Matrix. I'll be your moderator for this session, and we have a fantastic talk coming up in this session titled Application of Artificial Intelligence for Spermatogenic Staging Assessment in Rodents. To present this talk, we couldn't have asked for a more qualified speaker than Dr. Diane Creasy. Many of you will know Diane from her years of active participation in the STP before she retired and moved back to the UK in 2017. Diane's career in toxicologic pathology spans almost 50 years, starting out as a histology technician at Wellcome Research Laboratories in 1967 and moving on to Envigo Pathology in the US and finishing up with running her own consulting company in the US and currently in the UK. Much of her career has been dedicated to specializing in male reproductive pathology. In addition to providing consultancy on testicular toxicity, Diane has conducted several courses and delivered several talks on testicular toxicity. She has conducted several training courses on how to evaluate testes and interpret data from reproductive studies. She has also authored numerous publications on this topic, and her expert inputs have been crucial in the development and validation of this solution. She'll be speaking today about the rationale behind the solution development, its application, and the results. Diane will be joined by Mr. Nitin Singhal. Nitin heads product development at AIRA Matrix and is a technology professional with a track record of developing a repertoire of innovative AI-powered imaging applications. He'll talk about the technology behind the solutions, steps in algorithm development, algorithm outputs, and the road ahead. A few housekeeping tips before we begin. All attendees will be muted during the event to ensure quality of the audio. If you have any questions, please type them in the questions box and we'll be happy to discuss them at the end of the webinar. An email will be sent to all registrants with a link to the on-demand webinar recording within 24 hours after this talk concludes. So let me begin with a quick introduction to AIRA Matrix. Please bear with me, I'm having some problems with my broadcast. Right. So I'm sorry about that. So AIRA Matrix, we are a technology company, and what we do is we develop image analysis solutions and image management products and services for toxicologic pathology and discovery pathology, among other domains. We were founded in 2011 with the aim of developing automated solutions to optimize study reporting in toxicologic pathology. And we've been working in histopathology image analysis for close to a decade now. We are a team of 60 with expertise in different domains like pathology, machine and deep learning, data analytics, and productization. We work on a broad array of artificial intelligence-based solutions in collaboration with pharma companies, CROs, oncology hospitals, and academic research institutes across the globe. We develop products and provide services for domains like toxicology pathology, essentially for screening, triaging, grading, and management of study images. We work in the discovery pathology area for accurate quantification of efficacy models. In oncopathology, we work on disease diagnosis, stratification, and prognostication. In the microbiology area, what we do is develop solutions for microbial colony counting and analysis. And in the ophthalmology domain, we work on solutions for disease screening, monitoring, and prediction. So in essence, we work on the whole gamut of the spectrum, from simple quantification and grading to predictive analytics and precision diagnostics. We aim at moving beyond the conventional digitization paradigm of machine and deep learning. We work on harnessing the true potential of AI with applications not simply for automating routine manual tasks, but for improving operational efficiency and reducing costs by providing optimized workflows, as well as providing predictions and insights by analyzing and correlating the vast amount of information that can be extracted from multimodality data. We work on a platform-based services model to provide solutions for pathology image analysis using AIRA, our AI-based image analysis platform. This platform-based model ensures expedited development of custom solutions and efficient deployment of off-the-shelf products. The platform model also offers other advantages like effective extension and translation of developed networks across tissues, across other species, and different staining methods. As I mentioned, our solutions are aimed essentially at serving three goals: automating manual processes, improving the efficiency of laboratory workflows, and making predictions from analyzed data. In the automation area, we've worked on solutions for tumor stroma separation, detection and quantification of hepatic steatosis, hepatic fibrosis, severity scoring of rodent progressive cardiomyopathy, quantification of nuclear and membrane biomarkers, etc. On the workflow efficiency side, our solutions like tissue triaging systems for toxicology pathology slides, automated staging systems to aid multiparametric evaluations in reproductive toxicology, solutions for quantification of disease models like acute and chronic lung injury, among others. On the predictive analytics side of things, we work primarily on precision diagnostics with a recent foray into predictive toxicology and predictive microbiology. We collaborate with clients in pharma and CROs to develop AI-based image analysis solutions tailor-made to their specific needs on a services model. The collaborative services model ensures that we correctly understand and translate client requirements to productized solutions, offering deployment and licensing options commensurate with available infrastructure and resources on the client side. So in addition to the solution that we will be presenting today, we are currently collaborating on other developments in the reproductive toxicology space, like spermatogenic staging assessment in non-human primates, estrus staging assessment in rodents, and identification and quantification of abnormalities in spermatogenesis in rodents. We plan on presenting these developments in upcoming sessions of this webinar series, so do stay tuned with us for further webinar announcements. With that, I'll hand it over to Diane to take us through the topic for this session. So over to you, Diane.
Well, hello everyone. In this short talk, I'm going to give you a brief account of how we developed and trained an algorithm to stage and annotate tubules in H&E stained rat testes. I don't have time to provide too much detail, so please take a look at the manuscript that's recently been published online in Toxicology Pathology for a full account. And here's the reference to it. So it's generally agreed that the most sensitive method for detecting testicular toxicity, particularly spermatogenic disturbances, is to perform a stage-aware evaluation of the testes. This not only is the case in studies where testicular toxicity is expected to be seen, but I would recommend that all testes, whenever a pathologist looks at them, should be examined in a stage-aware manner. If they're not, then subtle but very important germ cell changes will be missed, and they'll show up later. So this generally requires that the pathologist be trained and experienced in staging, but also have a good working knowledge of the different germ cells that are in the individual stages so that they can identify when there's depletion or abnormalities there. And although formal staging is usually carried out on specially prepared PAS stained sections, a simplified method of staging can be carried out quite easily on H&E stain sections. And of course, those are available in most routine studies. So our main objective for this project was to develop an algorithm that can identify and sort the tubules from a section of rat testis into the different stages of the spermatogenic cycle. The questions we were faced with was, should we use a PAS or an H&E stain section? Could we actually manage to identify each of the 14 stages? What criteria would we use to separate the stages? And would the ultimate precision and accuracy be acceptable? We rapidly decided to use H&E sections, partly because PAS is a very inconsistent stain. Sometimes it stains the acrosome, other times it doesn't. But also because H&E sections are readily available and you can see the characteristics of staging at lower powers than with PAS. With PAS, you often need oil immersion to be able to see the acrosome detail. We did find that we needed to pool some of the stages to improve the precision, but that's because H&E is inherently a slightly less accurate means of staging. So the way we went about developing and training the algorithm was to start off with some basic staging criteria. That was the presence or absence of round spermatids, the shape and position of the elongating spermatids, and the presence or absence of residual bodies and meiotic figures. That was used to develop a preliminary algorithm, which we tested out on 15 whole slide images, and these all the tubules in each of those images were annotated independently by the algorithm and by the pathologist. We then compared the results and identified where the major discrepancies were occurring, and there were significant discrepancies early in the algorithm development. So to improve that, we added additional criteria, and these involved the relative numbers of spermatogonia and the increasing size of the packetine spermatocytes. That was used to improve the stage identification, and we also developed a decision tree to aid in the decision making of which tubules went into which stages. What we also did was calculate the stage frequencies for individual animals. This was done both for the pathologist and for the algorithm. And we compared this with the published stage frequencies for PAS stained testes. This had two uses. One, we used the data to decide which stages to pool to try and improve the accuracy of the staging. And the others was to be able to compare the H&E staging with the gold standard PAS staining. So once we'd improved the algorithm, we tested this out on an extra 5 testes just to confirm the reliability of the new criteria that we'd developed and that the staging pools that we were putting together. Once we were happy with that, we then entered into the validation phase of the project. This was done on an extra 13 testes, and these were staged and annotated by the algorithm. But in this case, whereas the training of the algorithm was done blindly, so the algorithm would stage the tubule and the pathologist would stage it independently, we decided to do it slightly differently. We got the algorithm to stage the tubules, and then the pathologist would go in and either agree or disagree. And I'll show you why we did that shortly. So by doing that, they corrected, either agreed or corrected the stage identification using a second annotation. And once we'd completed that, we calculated the accuracy and precision of the algorithm. So these were the images, the annotated images that we used throughout the project. So you can see here the scanned image, and the algorithm has gone through and staged each of the cross sections of tubules here, put a different color around to distinguish which of the stages or which of the group of stages it's put them into. and then and also if you hovered over the annotation, it would tell you which stage it was. Then the pathologist went through independently and put a separate annotation by a square annotation in the middle and said what they thought it was, and then we compared the two stages. So these are the actual staging criteria, the improved staging criteria that we ended up with for the H&E testes. I haven't really got time to go into them in detail, but this table is in the manuscript, so you could go through it later. But in summary, stages 1 through to 6 were determined by the position and the bundling of the elongating spermatid heads as they started off in stage 1 at the lumen, moved down in stage 4 to 5 to the base of the tubule, and then moved back up to the lumen. Stage 7 and 8 were distinguished by the size, position, and characteristics of the residual bodies. Stages 9 through to 13 were basically just depending on the shape of the elongating spermatid head, and stage 14 was identified by the presence of meiotic figures. So I'll show you these in actual sections. Here's a stage 1 section, and you can see that most of the elongating spermatid heads are fairly randomly distributed around the lumen of the tubule. They haven't really started going down into the epithelium yet. Some of them do, but the majority are up at the surface. Once we move into stage 2 and 3, the elongating spermatids are starting to bundle and the heads are starting to move down into the epithelium, but most of them haven't got down to the base yet. Notice around the base here how few spermatogonia there are. There's one there, there's one there, there's one there, one there, but they're fairly spaced out. This was an important criterion to distinguish this from stage 5 to 6. So here's stage 4 to 6. We had to pool a number of stages here to get the sort of precision that we wanted. It was difficult to decide where one stage stopped and the next stage started. But this would be effectively stage 4 to 5, when the elongating spermatid heads are right down towards the base of the tubule, and some of them are actually touching the Sertoli cell nucleus. Coming back out of this stage, we're now entering into stage 6, and you can see that the elongating spermatid heads are coming off the base and they're moving back up towards the lumen here. But you can see how difficult it is to decide when you call this a stage 6 versus a stage 5 when some of them have started moving out, and that's why we ended up pooling the stages together. So stage 7 and 8 were distinguished on the residual bodies, and this is very early in stage 7. The residual bodies are hardly even evident here, but all the elongating spermatid heads are up at the surface, and the residual bodies are just starting to form and move down the tail. Whereas halfway through stage 7, you can see that they're very much better formed, and they're all starting to move down the tail towards the head. In stage 8, the residual bodies become much more condensed, bigger, and they've moved down to below the elongating spermatid head up at the surface here. And by the time you're coming back out of stage 8, they're starting to be shed, because this is the stage of spermiation, and leaving the residual bodies behind at the lumen here. Now this tubule is coming out of stage 8 and entering into stage 9, and the round spermatids are just starting to lose their round shape, but there's still a few elongating spermatids along the lumen here. So this is where we found the difficulties of deciding where exactly one stage would finish and one stage would start, and this is why we ended up pooling a number of stages, and also why we ended up doing the validation non-blinded. So for stage 9 through to 13, we were just looking at the shape of the elongating spermatid heads. Here they are just starting to lose their round shape, and become oval. Here they're elliptical. Here they're becoming banana-shaped, and then they move into a sort of scimitar shape, which gets thinner as it moves through to 13. Again, we found it very difficult to draw a line between 12 and 13, so we pulled those. And then stage 14 was just whether or not there was at least one meiotic figure in the tubule. This is right in the middle where we've got both meiotic divisions going on, the secondary spermatocytes, round spermatids, meiotic figures, as well as diakinetic spermatocytes. But as long as there was one meiotic figure, we could call it a stage 14. So once we'd sorted out the final criteria, we started doing the validation of the algorithm. This was done on an extra 13 testes. And in this case, the algorithm went through and assigned a stage to each of the tubules. And again, you can see the color here is determining what stage it was in. I would then go through, look at the stage, decide whether I agreed with it or disagreed with it. If I agreed with it, I would just put a blue square in the middle of the tubule. If I disagreed with it, if it was just too far away from what the algorithm was calling, I would put a red square in it and I would correct the stage. Some of them you can see have got yellow squares. This is basically where the tubule was tangentially cut. It didn't have a good enough section for staging. So basically it was unsuitable for staging. So when we finished the validation, we needed to get the performance characteristics of the algorithm. And this is a confusion matrix. Basically, for each of the staging pools that we were measuring, this number that is highlighted is the number of tubules where there was total concordance between the algorithm and the pathologist. So for example, in stage 11, 301 tubules, both the algorithm and I called stage 11. However, two of the tubules the algorithm called stage 12 to 13, and another two it called 10. And you can see for most of these stages, it's either plus or minus one stage that the algorithm is called, and there's very few tubules. The vast majority we were in complete agreement with. You'll see there's a bit more variation up here, particularly in stage 2 and 3, which was difficult to distinguish from some of these others. But even so, the numbers are still relatively small, and they're mostly plus or minus one stage. So from that data, we calculated the precision and the accuracy of the algorithm, and we were pretty happy with these results. So for most all of the staging pools here, it's over 98% concordance. The main one, this one is slightly lower at 93%, but that's still not bad. And the overall accuracy was 0.9884. So we were relatively happy with that. We also calculated the stage frequency for individual animals. And so these are the different pools of staging. And for each animal, we would calculate the frequency of the stage in the section and then draw up the mean, the standard error, and compare them. So obviously the algorithm and the pathologist are pretty close, but this is the numbers that Hess produced for PAS stained sections. And this is really the basis of how we decided whether we were getting adequate precision on all of the stages and how to pool the stages. So you can see it's pretty good right the way through there. So how can this application be used? The algorithm will automatically stage and annotate all cross-sections of tubules in an H&E stained testis. This facilitates the pathologist to perform a stage-aware evaluation. What it doesn't do is to identify abnormalities in the testis, and it doesn't identify stage-specific abnormalities. That is still down to the pathologist. And so it's still important for the pathologist to have a good understanding of that normal germ cell complement so that they can identify when there are actually abnormalities, either germ cells missing or depleted, or for instance, spermatid retention. It can rapidly pick out all the tubules in a given stage. So if the pathologist thinks that they can see some spermatid retention going on, rather than just hunt all around the testis for the appropriate stage to examine it, they can pull out all of the stage 11 tubules and go and check whether there's spermatids retained around the lumen. Or if they think that there is a stage-specific germ cell degeneration, for instance, maybe the meiotic spermatocytes look as if there's increased degeneration there. You can pull out all the stage 14 tubules and go and check whether the suspicion is correct or not. You can also rapidly calculate stage frequency, but only really if you suspect there's a disturbance there. I wouldn't recommend doing this on a routine basis, because no one really knows if there was a change there, what it means anyway. Stage frequency is just measuring stage duration. But if you're looking at a testis and you think maybe there are not enough stage 14s, you haven't seen the number you normally would expect, you can do a stage frequency and you can compare it with the control. So you can do that very rapidly. Another potential feature, which we haven't yet validated, is that we could quantitate the number of germ cells. For instance, spermatogonia, Pachytene spermatocytes, round spermatids, and that could be a very powerful feature for the future. So, but we're still working on that. So in summary, an algorithm has been developed that can stage, sort, and annotate the seminiferous tubules in an H&E stained rat testis. It can sort the tubules into 10 pools of stages, that is stage 1, 2 to 3, 4 to 6, 7, 8, 9, 10, 11, 12 to 13, and 14. It's got very good accuracy and precision, over 98% for accuracy and over 93% for precision. And the algorithm facilitates a stage-aware evaluation of spermatogenesis to be performed on H&E sections. The algorithm also allows a rapid stage frequency analysis to be performed if needed. Okay, thanks. I'll be happy to answer any questions in the Q&A, but I'll hand it over now to Nitin Singhal, and he can describe some of the technical details of the algorithm.
Thank you, Dr. Diane. AI in life sciences. Artificial intelligence, or AI, is a dynamic force that is reshaping our lives, our environment, and our interactions. It can be described as a program whose aim is to generate and potentially even improve on human-like cognitive processes. As the world is grappling with unprecedented times owing to COVID-19 and a looming health crisis, the need to innovate and rapid adoption of AI and automation is tremendously high and is being felt across various life sciences functions. At AIRA Matrix, we strive to reimagine AI and machine learning. Today, AI has progressed from few lines of codes to more integrated and complex neural networks that are enabling deeper learning and insights. This is where our ongoing efforts are focused. A multidisciplinary group of people at AIRA Matrix are working on several programs where insights from data-driven machine learning is fused with domain-specific knowledge to amplify the quality as well as the causal veracity of the predictions derived. Our state-of-the-art capabilities in computer vision, machine learning, deep learning, knowledge representation, and reasoning are used to robustly predict the required information. Some key challenges we tackle include lack of sufficient labels needed for traditional supervised learning, the need to ingest and link multiple data modalities, efficient deployment of complex deep learning models, and the need to build AI solutions that are interpretable. We are creating an AI-driven virtual staining system that can produce virtual immunostains from existing H&E whole slide images. We are developing few-shot, zero-shot, class imbalance learning systems that learn from minimal labels to predict behavior. DL models are huge in size with millions and billions of parameters and are challenging to deploy on edge devices. We are using knowledge distillation to perform model compression by teaching a smaller neural network using a bigger, already trained network. Our researchers and engineers are constantly aiming to apply these state-of-the-art solutions in different aspects of life sciences. For example, augmenting pathologists by increasing workflow efficiency to save precious time. Getting back to spermatogenic staging, the figure shows here the main step that constitutes the algorithm pipeline. Some key elements of the algorithm includes active learning to interactively query an expert pathologist to label new data points with the desired outputs, segmentation of the individual tubules, segmentation of the lumen and various germ cells like spermatogonia, spermatocytes, round spermatids, elongated spermatids, meiotic bodies, and residual bodies, a 28-dimensional feature vector corresponding to each tubule, and a decision tree-based classifier which is generated using the feature matrix. A growing problem in machine learning is the large amount of unlabeled data, since data is continuously getting cheaper to collect and store. This leaves data scientists and engineers with more data than they are capable of analyzing. That's where active learning comes in. Active learning is a learning algorithm which can query an expert interactively to label data with the desired outputs. In active learning, the algorithm proactively selects the subset of examples to be labeled next from the pool of unlabeled data. The fundamental belief behind the active learning concept is that a machine learning or deep learning algorithm could potentially reach a high level of accuracy while using a small number of training labels if it were to allow to choose the data it wants to learn from. As shown on the left image, a trained junior model annotates samples from an unannotated sample pool. Then selects those with high uncertainty and asks the human expert to annotate or correct those annotations. With expert annotated, the junior can learn more and become a better trained model. With this better learning and training, the trained model is supposed to have higher ability to annotate the remaining unannotated samples from the pool of data. With the above framework, we were able to save 3x the effort of a human pathologist. We present HistNet or histopathology network, which uses an encoder-decoder architecture similar to UNet as seen on the figure in the right. The encoder network incorporates inception-like modules, which provide the capability to aggregate contexts to extract complex features for identifying tissue cell morphology as the feature maps are downsampled. The decoder network uses a dense shortcut connection for better propagation of information between layers. Additionally, the network uses parallel convolutions to enhance context aggregation. The proposed architecture achieves better segmentation performance than most state-of-the-art segmentation models while using a significantly lower number of parameters. Data used in this work consists of a set of whole slide images of rat testis. Our training data included 20 and a validation data set comprised of 13 images. The annotations were marked to identify pixels, regions belonging to lumen, various germ cells, and tubule level staging. Table here summarizes the DICE performance achieved using our algorithm pipeline. The DICE similarity coefficient, also known as the DICE coefficient, is a statistical tool which measures the similarity between two sets of data. Here, two sets of data are ground truth label marked by an expert pathologist and the predictions by the algorithm. As can be seen, the algorithm achieved significant overlap with the ground truth labels. Here we show the results of our segmentation algorithm at different stages. System outputs pixel level overlays for various germ cells. A pathologist can use these overlays as a second read to confirm that no area from the image is missed from the analysis. In addition, The algorithm can also calculate the quantification of number of different germ cells present in each of the tubule. Both the overlays and the quantification of germ cells makes our algorithm pipeline interpretable. Figure here shows tubules annotated by the algorithm on an H&E stained section. Each appropriately sectioned tubule is outlined using a different color, depending on the stage identification assigned by the algorithm. We achieved high agreement between AI algorithm and manual assessment on H&E stained images, thus eliminating the need for preparing additional PS stained slides for spermatogenic staging. In conclusion, our algorithm provides objective, accurate, and precise spermatogenic staging with rapid turnaround, can potentially be used as an effective evaluation tool in male reproductive toxicology studies. Our roadmap includes development of method to identify stage-specific degeneration or absence of germ cell, as well as the inappropriate presence of germ cells, for example, in spermatid retention, that might be caused by testicular toxicants. With this, I open the floor for questions.
Sure. Thanks, Nitin. Thanks, Diane. And yes, there are several questions specifically addressed to Diane. So, Diane, I'm just reading out the questions and take it from there. So there's one saying, thank you for the wonderful work and great presentation. Can you ask Dr. Creasy if she envisions this tool as screening tool primarily, that is screening out discordant stage frequency with concurrent control? Can you give an example with a case study, if any, performed, or a hypothetical scenario?
So if I understand the question correctly, you're asking for an example of when one might use the stage frequency map or calculate the stage frequency. I've always been of the opinion that you probably shouldn't be calculating stage frequencies. Certainly previously people were generating some stage frequencies for certain stages and putting those into a report and saying that that meant that they had done staging. What it does do is measure the duration of a particular stage. So if you increase the duration of that stage, you'll see more tubules in that stage. If you decrease it, you'll see fewer tubules. So in theory, if you did the analysis and compared the treated group with the control group and you found far fewer, for instance, stage 14 tubules in the treated group, it would suggest that stage 14 was happening a lot quicker. If that was the case, then you would expect another stage, maybe either side of it, to be longer in duration. It's not going to get rid of it, it will just change the duration. I don't actually know of any examples where that's happened. However, no one's really bothered to test it previously, so it's conceivable that it can happen as a treatment-related change. The worrying thing is, what do you do with that data if you actually measure it? But it's something that can be measured. As I say, I wouldn't recommend doing it, but I know sometimes I look at a testis section, I think I can't see any stage 14 tubules. Where have they all gone? And you have a feeling that there may be rather fewer there, but this would give you the opportunity to test it out.
Right. Thanks, Diane. There's one more here. How variable is the number of non-evaluable tubules per section? The sections evaluated are beautiful, but for many studies, they are not so consistent. Does the algorithm recognize rete testis? Did you look at any testis with focal disruption of tubules at the periphery?
There were surprisingly few tubules that were not stageable. In fact, the algorithm went ahead and tried to stage more tubules than I would have done. But as long as you've got a good cross-section, and the important thing is to get most of the tubules as cross-sections, it probably can stage longitudinal sections, but of course you're likely to get more than one stage in them. So we specifically decided not to include those in the staging. So you really need a nice cross-section through the whole testis to get the majority of tubules that are stageable. In terms of poorly prepared testes, that I have to say we haven't. I mean, I'm certainly aware that not all testes would end up being as good as that, and it would probably struggle with very certainly poorly fixed testes. But it seemed to be actually quite robust in being able to stage tubules. So we haven't done the study to find out, how poor a section you can get away with. And as for abnormal testes, no, that's something else that we're working on separately to identify abnormalities. So we've discussed what the algorithm would do with, well, actually I think we have tested it out on some testes. So even if they have got abnormalities so far as, for example, spermatid retention, it will still be able to stage the tubule. And even if it's got some depleted germ cells, it will still be able to stage the tubule, unless, of course, you've got massive germ cell depletion. So even if there are slight abnormalities, it will still go ahead and stage the tubule, which means that the pathologist has still got to pay a lot of attention to make sure that they pick up the abnormalities.
Right. Right, thanks, Dan. There's one more question here. This appears to be a well-validated staging algorithm. The question could be raised whether reduction from 14 to 10 stages decreases the sensitivity of detecting spermatogenic alterations. Has the algorithm already been tested on testes with altered spermatogenesis?
I would say it wouldn't change the ability, as long as the pathologist knows what they're doing, then it's not going to alter the ability of the pathologist to detect those spermatogenic abnormalities. Because I find that if you can just stage tubules into very early in the cycle, midway through the cycle, or late in the cycle, and stage 14, that's enough to be able to evaluate the numbers of germ cells and the appearance of germ cells. To get the very detailed, for instance, if you've got misshapen elongating spermatids in stage 12, you really need to know what shape those elongating spermatids should be to say that's not normal. If it was stage 11 or something, it would look different. But very often you can get abnormalities in stage 12 and 13, where you get a shape of elongating spermatid that is just totally abnormal. You never see it in any of the stages, but it's up to the pathologist to know that. I don't think that pooling these stages in the small groups that we have is a problem. If you look at it, you identify that there's an abnormality and you want to know really the specific stage it's happening. If it's only a single stage, then you would need to go do a PAS stain and look at it manually. So you can go back and look with PAS, but I'm fairly happy that the pooling of the stages that we've got doesn't really desensitize the whole thing. And what was the last bit of the question? Had we tried it on abnormal testes?
That's right. That's right.
Yeah, which we have, and it depends how abnormal it is. As I say, it will go ahead and still stage the tubule to the best of its ability. So it still needs a lot of input from the pathologist. What this does is the ability for the you know, if you're going to do a stage-aware evaluation, this will tell you what the stages are, but it's still, a lot depends on the pathologist being able to evaluate those stages and know when there's something wrong with them.
Right. Right, and then there's one about the training and testing slides, where the training and testing slides belonging to different studies, and slides from how many different studies were included in the training set. And did you try to test your algorithm on lesion slides where the stages were still correctly picked up? I think the last bit you've already answered, but the first one, where the training and testing slides belonging to different studies, and slides from how many different studies were included in the training set.
The slides were all taken from a single study that had been set up to evaluate differences, I think, between different age animals. So all of the animals were sort of normal. There were different ages and so on. We took testes from a subset of this very big study that were all of a specific age, and all of the testes were taken, the training set, the test set, and the validation set. So they were effectively all from the same study, but within that age range of rats.
Right, right. There's one question more on the prostate cancer side of things. Maybe I can take that. Can the model be used to correlate prognosis, 5-year life expectancy in prostate cancer? Any correlation study performed for clinical consideration used for prognosis? So no, we haven't used this model for prostate cancer. However, we have a separate model for Gleason grading in prostate cancer. And yes, we are working on the prognostic and the predictive indicators on the prostate cancer side. We have a paper out for Gleason grading, the model that we use for Gleason grading. And after this session, I'll be happy to share that paper with you. All right. There's one more.
Good.
Yeah.
Go ahead.
Yeah, thanks for a very informative session. Great work by the team. How many samples are enough to validate the algorithm? Do you think the same solution can be used in other studies, or does it require altering that region of interest? Nitin, do you want to take that?
So we have validated it. Basically, when you talk about 13 whole slide images, the number of tubules are quite large. So we have currently validated on 13, but as Dr. Diane said that most of the images have come from a single study. Our next step includes basically analyzing and validating the algorithm on multiple studies, so that we can incorporate that variability into the algorithm.
Right. Yeah, Dr. Creasy, did you try the AI on different species like dog, non-human primates? If not, are you planning to? So, yes, Dan, please go ahead.
Well, I was just going to say we certainly AIRA Matrix is working on the non-human primate at the moment, and perhaps Uttara can address that. Dog, I think we did think about doing it in the dog, but the dog is just got so many background lesions, and very often the efficiency of spermatogenesis is relatively poor in some animals, it's good in others. The spermatogenesis is nowhere near as regular as it is in rats. So the rat is by far the easiest species to use. Monkey is probably second best, and dog is pretty awful. So I don't know whether we're even going to. Just the pathologist finds it difficult enough to stage a dog testis anyway. In H&E, well, you can only do it in an H&E section because of the acrosome doesn't stain up with PAS. So it's only a very rough and ready staging that the pathologist can do. So I'm not sure how useful it would be for the for an algorithm to do it, but we're not considering it at the moment. But maybe Uttara can address the non-human primate.
Right. So we are working on spermatogenic testing in non-human primate at the moment, and that algorithm is proceeding very well, and it's shown us good results. The algorithm is in the testing and validation phase, and we'll keep you posted on that one. In fact, we will be presenting a webinar soon on the non-human primate spermatogenic staging as well. So we'll keep you posted on that. So there's one more. Dr. Creasy, did I understand you correctly? Did the AI recognize single cell types / forms, 28 ones, and then decide the stage by how many of which are in there? Or are the 28 vectors per tubule, Dr. Singhal mentioned, more abstract factors at both, in a sense, Diane and Nitin, do you foresee further adaptations and improvements of the algorithm with broader use, thousands of testis, different ages and strains of rats? So,
Yep.
who
So
wants to take this? Nitin, yeah.
I'll take the first question when you say about the 28-dimensional vector. I agree. This is more like an abstract factor. It is not purely a rule-based or a threshold-based analysis. The factors are basically mentioned in the manuscript, as well as in Diane's presentation. It was shown what are the different factors which we have taken into account for determining a particular stage. This 28-dimensional factor is an abstract form of that those factors.
Right. Right. And do you foresee further adaptations and improvements of the algorithm with broader use, thousands of testes, different ages, and strains of rat? Well, yes, we do. We do see, extending the algorithm to other strains of rats, other strains of rodents, as well as other animal species. As I just mentioned, we are working on non-human primates as of now, and we are open to other collaborations to work on similar algorithms on different animals. Right. So there's several actually, yes. How about the fixation? How do you predict the algorithm performs in formalin fixed testes?
I would imagine it would do it pretty awfully. we don't know. It is very difficult to see because this algorithm relies quite a lot on seeing the elongating spermatid heads in the early phase tubules, early stage tubules, and also the shape of the elongating spermatid heads in the late stage tubules. So I don't think you're going to see things like that in formalin fixed tissue. So I wouldn't recommend even trying it on formalin fixed tissues.
Right. Then there is another interesting question. Does the staging performed correlate with any biochemical parameters like serum testosterone levels?
I mean, theoretically, the stages 7 and 8 are the stages that are most responsive to testosterone. They have the maximum number of testosterone receptors and so on. So there are different things that happen in different stages, but you would need to know what those things are. For example, FSH is, or the tubules that are most responsive to FSH are the ones that are in stages 1, 2, and 3, I think. Stage 7 and 8, they're responsive to testosterone. But there's no sort of direct correlation. It's just a matter of knowing the physiology of what happens in what stages.
Right, right. There's another question. How does the algorithm perform when there are lesions like necrosis of spermatogenic elements?
If the damage in a testis is too severe, then I think it's just going to not be able to stage. To be honest, I don't think we have tested that. We've tested it on some quite subtle spermatogenic disturbances, as much as anything as a part of the development of trying to pick up abnormalities in spermatogenesis. And it still seems to be able, as long as the disruption to spermatogenesis isn't too severe, it can still adequately stage the tubules. But we haven't really tried it on significant damage. I think that would be up to the pathologist to identify that really. And if you're looking for stage-specific changes in the testis, then by definition, you've got pretty subtle changes there. And you're looking for, you're not looking for dramatic depletion of cells, you're looking for very subtle depletion of cells. So I think that this needs to be used on not very badly damaged testes, basically.
Right. Right. Then there's one more, how to report or measure spermatid retention. Also, is it possible to evaluate Leydig cells?
So how to report on spermatid retention? If the algorithm, I mean, what the algorithm will do is just identify stage 11. Generally, I find that you pick up spermatid retention most easily in a stage 11 tubule, and you'll see the mature step 19 spermatids at the lumen above the step 11 spermatids. And so that you see that they're there. The pathologist has still got to do that. What they need, the way the staging algorithm could be used is the staging algorithm will highlight or sort out all the stage 11 tubules so that the pathologist can look at them. Alternatively, it can pull out all the stage 12 and 13 tubules and see if there are any of the step 19 mature spermatids down at the base that have been phagocytosed down. So it quickly sorts all those tubules out, but it's down to the pathologist to be able to identify the abnormality. What was the second part of the question?
No, I think that was it, Diane.
Oh. No, that was how to report spermatid retention, and then there was something else.
No, I think that
Leydig
was the question.
the Leydig cells.
The Leydig
Leydig
cells. You can identify Leydig cells. Yeah.
No, we didn't do anything with Leydig cells there. I mean, they're not too difficult to identify anyway. It would be nice to pick up the difference between Leydig cells and macrophages, but no, it doesn't do that.
We do have another algorithm that does identify normal cells in the testes. So yes, we can identify Leydig cells, but we haven't incorporated that one in the spermatogenic staging algorithm. So to answer your question, yes, we can identify Leydig cells as well. Then there's one more. How many experts reviewed the stages?
Only one. I was the only person working on it. We decided that was quite important because, as many of you that do staging know, it's something of an arbitrary thing anyway. You can have two experts together, and they'll probably call, for instance, stage 12 and 13, where they decide that the line is, the boundary is, can be quite different. When I used to do this with Bob Chapin, we had slightly different views on the exact characteristics of stages. So if we had two people doing this, we decided there would be too many variables. And this, to some extent, is why we decided when we did the validation part of the study, not to do it blind, because I know that sometimes I'll look at a tubule if it's right on the transition between one stage and another, and one day I would call it the one stage, the next day I'd call it the other stage, because I was just concentrating on slightly different criteria. So at least we cut down on that variation by just having the one expert to do the staging.
There's a related one here, Diane. Dr. Creasy, are you planning to test the AI blinded? And a related question, do you know what the interpathologist agreement is on such staging? Or more importantly, do you have an idea for a way to find a ground truth on staging which is independent of the human pathologist? So maybe Nitin and Diane, I think both of you need to answer this one. So Diane, starting with, are you planning to test the AI blinded, and do you know what the interpathologist agreement is on such staging?
We weren't aiming to test it blinded. I was fairly happy going through those algorithm stage tubules that I could see. When it's right in the middle of a stage or a staging pool, there's no problem at all. But once it starts to get towards the next stage or the next staging pool, it's very difficult to say, right, I'm going to call it this, but there are no set criteria to call it. So it's more a sort of judgment thing. And if it's just a judgment thing, we certainly felt that if the pathologist looks at it and says, yes, that the stage that has been called there, I would be very comfortable calling it that, then it was called that. But to try and arbitrarily, as I say, if you did the same pathologist on 2 occasions, it would be different because they just wouldn't be that consistent. So I'm sure there's quite a lot of difference in the consistency if you took 2 or 3 pathologists and got them to stage it. And probably the same with the female reproductive system. You ask people to try and stage the estrus cycle in the rat, and you'll come up with a lot of different answers because they're concentrating on different criteria. So we're not aiming to do it blinded.
Right. And Nitin, do you want to take this one, or more importantly, do you have an idea for a way to find a ground truth on staging which is independent of the human pathologist?
I think so. Currently, we are very confident the algorithm is performing, as Dr. Diane has showed, that it is performing to accuracy of more than 98%. So in the current form, at least on the normal testis, we can test this algorithm, which will generate ground truth. And the results will be very similar to the ground truth done by a human pathologist. Moving forward, we plan to improve the algorithm, including different abnormalities of testes, like spermatid retention and those kind of things. So we should be able to generate an algorithm which generates a good agreement with the pathologist, and that can be used for generating basically the spermatogenic staging.
Right. Yeah, I'm sorry, go ahead.
I was just going to say, I don't think, since staging is a very sort of arbitrary thing anyway, it's a continuum, and there are no set criteria as to where one stage starts and one stage ends. It's very much done on the majority. Even if you did it on a PAS section with acrosomes, some of the spermatids with acrosomes will have moved on to the next stage, and some of the spermatids in the same tubule won't have moved on. So are you going to take the ones that have moved on a bit further, or the ones that are delayed? The whole thing is a continuum, and so there are no set features that you can do. So the whole thing is a human construct in the first place. I think it's got to depend on the human staging and get the algorithm to just hone in and be more consistent, if you like, because one assumes that the algorithm is going to be more consistent than the pathologist would on a day-to-day basis.
Right. Then there's one more question. I think you kind of answered this. Which proportion of tubules in an entire cross section were not sufficiently transverse and could not be used for staging?
I'm sure we have the capability of checking that, but it was very small. I don't know, Nitin, could you hazard a guess as to how many?
Yeah, so I agree. It was a very small percentage. I don't have the exact percentage, but it was 1 or 2 tubules in a single whole slide image is what we get.
But maybe the algorithm did 1 or 2 tubules, but I probably did a few more. So I would say, I mean, we had one of the slides there, I think the algorithm had already thrown out a few tubules there, and I threw out a few more. I would say there was probably, in terms of the cross sections, I would say under 10. And since a testis cross section like that has probably about 550 to 600 tubules, 10 out of that many is not a large number.
Yeah.
Right. Right. And I think the final two questions I'll address. Any pointers how one can get access to this algorithm and software, and what will be the hardware requirements and any commercial use of this model? So yes, definitely, I'll write back to you regarding access to the algorithm and the deployment side of things, and what would be the deployment options and the hardware required, etc. And yes, definitely, this algorithm is very much looking at commercial use in the near future. So okay, there's just one last question now. Dr. Creasy, do you think there's a large benefit in having 10 pools versus maybe 3 to 4 or even only the 2 most important stages? There was another question about, why not 10 stages? Why not 10 stages instead of 14? And then there is this question now about, is there a large benefit in having 10 pools versus maybe 3 or 4, or even only the 2 most important stages?
Yeah, I can see why that question's being asked. I would say, as I said a little bit earlier on, I find it's pretty much adequate if you know, let's say, the beginning of the early. So if we divide the 14 stages up into stages 1 through to 6, mid stages 7 and 8, and then the later stages up to 14, and then you've got stage 14. So that's, if you like, 4 pools of stages. And I would say that that is pretty good to be able to do that, to be able to pick up most abnormalities. So this goes above and beyond that. It brings it down a little bit more. Stage 1 is actually quite frequently that is affected. So it's nice that that one's pulled out separately. So I think the main advantage is to be able to separate it out into, if you like, those 4 stages, and I think that that will give you most of the knowledge that you need to be able to identify abnormalities. This does more than that, so it could be of use, but in truth, there's relatively few abnormalities that are going to home in onto one specific stage unless you're doing a very, very specific investigative study. They're going to affect more stages than that. It's important to be able to pick out 7 and 8 because that can certainly have stage-specific effects in 14 and 1, and then the rest, and stage 11 for spermatid retention. So you can certainly do with less stages.
Right. Right. I think, and then with that, we've kind of addressed all the questions. So I think we'll end here. Thank you, everyone, for joining us today. You can always write to us for any further queries or on this solution or any of our other services. And we do look forward to a similar interaction, a similar enthusiastic interaction with you in our next session in this series on AI applications and reproductive toxicology. Meanwhile, do take care of yourself and stay safe. And goodbye to the next one. Thank you.
Thank you.
Thanks.